before we get too carried away, we have to remember that we came here to listen to PIs talk, and not just aspiring PIs, but we have some regular PIs that are also going to give some experiences that they have in cyber-physical systems research. So this is an opportunity to see the kinds of things that have already been accepted as and funded as part of the solicitation. Before we move on to that, I want to address a couple of really common questions that I got in the break. So anybody want to guess what the most common question that I got over the break was? When's lunch? No. Good guess, though. Later. Are the slides going to be available? Basically, yes. So I'm not going to put them up now because even though I have a copy of them, I didn't check with David and Ted before they gave them to me that they were okay to post. And so they may have a couple of things they need to do, or they may need to put a disclosure statement or something. But my understanding is that if they're willing to be recorded, they're probably willing to share their slides. And so instead of emailing them to everyone, I'll put them on the VO and you'll be able to download them from there. And I know that the first two speakers and also Hadas are willing to share their slides as well so that you can see them. Basically, because everything's being recorded, we'll have all of those things showing up on the virtual organization over time. We're also planning to get transcripts done for the sessions that we're recording, so you can search those transcripts, not just for what's in the slides, but for the things that people actually say. And that may come in the most handy when it comes time to look at the panel sessions, because then you'll get to hear the question and the response, and that'll be really useful. The other most common question was about travel reimbursements. And so if you have questions about travel reimbursements and I haven't answered them yet, then email to me, because I'm forwarding those emails on to our folks that are checking to make sure that they have all the ducks in a row. And so, for example, if you don't have all the forms, you think you might not have all the forms, send me a mail and then we can cross-ref with what we have to make sure. So those were definitely the most common ones, but if anybody else has any questions right now, I can answer them. Lunch is later. There's more coffee after lunch. Okay, great. So in the meantime, I'll go ahead and introduce our first speaker, Andre Platzer, who received the undergraduate and master's degree in computer science from the University of Karlsruhe in Germany in 2004, and the PhD in computer science from the University of Oldenburg, Germany in 2008. He's now an assistant professor of computer science at Carnegie Mellon University, where he develops the logical foundations of cyber-physical systems to characterize their fundamental principles and to answer the question, how can we trust a computer to control physical processes? Andre.
Thank you. So you put me under a lot of pressure here because early on you said the talk has to be exciting. I'm not sure I can live up to that expectation, but I'll try my best. So this talk is about the logical foundations of cyber-physical systems, which is the same as the title of my career project, where the biggest question is, can you trust a computer to control physics? And I don't mean that in the sense of changing the laws of physics around, because they're somewhat unnegotiable, but in the sense of providing the right input into physics. And we've seen earlier this morning already what kinds of interesting things we can do with cyber-physical systems if only we could trust them. And we need to be able to trust them with our lives. I mean, we've seen this other question, how can we provide people with cyber-physical systems that they can bet their lives on, which is really the key question. So the rationale behind my research is, if we want to trust those systems, we need guarantees. We need guarantees about their safety, and guarantees don't come from out of nowhere. They come from strong analytic foundations. And the foundations certainly revolutionized all of computer science and indirectly all the way our society works. But we certainly need much stronger foundations as soon as this software that we're writing is reaching out into the physical world and affecting us directly, not just by way of the stock market crashing due to a software bug. Maybe the main motivational insight behind my research agenda is that cyber-physical systems, what they really mathematically are from a fundamental characteristic is CPSs are multidynamical systems, which means they're systems that are characterized by multiple facets of dynamical systems, not just one, but many of them. The most prominent ones that are being alluded to are usually, well, they're discrete dynamical systems, but simultaneously they're also continuous dynamical systems in what together we know as hybrid systems. But what I'm saying is really there's many other dynamical aspects as well in those cyber-physical systems. There's aspects that are of adversarial nature, you get adversarial dynamics, there's non-deterministic dynamics, and there's stochastic dynamics. The thing that saves us in those complicated cyber-physical systems is exactly the realization that, well, the whole system may be complicated, but there's many simpler pieces which are not so bad. There's, in this complicated system, there's a discrete phenomenon, and we can understand this discrete phenomenon in isolation. There's this other continuous phenomenon. Oh, that continuous phenomenon is not so bad. And the only reason why the whole system is complicated is because all of them mix and match. All of them are being combined together. In other words, cyber-physical systems are compositions of those multiple dynamical effects, but each of which is much simpler because it doesn't have to talk about the whole system all at the same point in time. It only talks about one particular effect. And by way of doing that, you also tame their complexity. So you have a complicated CPS, but it has tame pieces and tame parts. And you're exploiting this compositionality in order to make sure this overwhelming complexity of cyber-physical systems has any chance at all of being controlled. More of an illustration. Hybrid systems you've seen. For example, if you're controlling a robot, then it is following certain discrete dynamics coming from the control decisions, certain continuous dynamics coming from the differential equations. And you can control this robot safely by looking at the projected corridor ahead of you. And when this is clear, you say, I can move. And of course, interesting phenomena happen as soon as this robot hits another robot. Because then if one of the robots is just projecting ahead of him, what is the corridor look like, and the other robot does do the same thing, both of them might think that actually it's safe to move on. But of course, that's not the case because all of a sudden they get hit from the side. More generally, when you're controlling those systems, what you need to take into account is their multi-agent behavior as well. So what we have to take into account is the fact that there's other agents in the world. And one dynamical aspect that is underlying this is that of adversarial dynamics. So when one robot, let's call it the angel robot, is taking its various control decisions, what it has to make sure is it has to make sure that it will be fine no matter what the other robot is doing. That's a phenomenon that's never a discrete dynamical phenomenon. It's not a continuous dynamical phenomenon either. It's one of adversarial dynamics happening. I have to find one way of planning my actions that is fine for anything that the other agents around me will do. And if you do that, as soon as you take this dynamics into account, then the one robot will move and say, I'm not quite sure what the other one will be doing. I have to be safe regardless, no matter what control choices the other ones will be doing. And as soon as you take this perspective, which actually leads you to a hybrid game perspective, then all of a sudden, the control that your system is exhibiting will actually be fine no matter what the other agent is doing. And this is really just one illustration of why cyber-physical systems are multi-dynamical systems, not just hybrid systems, but they're often much more. And what do we see in this cyber-physical systems dynamics? I also call it the B because, I mean, I wrote down all those various dynamical phenomena, and they overlap in all kinds of ways and so on. And later on, I looked at it and said, that looks like a B. And of course, the CPS B sounds like a very natural fit to the CPS flower model because this is really the mathematical foundations behind all of these various things. So what we see up here in this intersection is the systems that are both of discrete dynamical nature and of continuous dynamical nature that are interacting and making things happen that you couldn't model in any isolated way. And these are the hybrid systems that have been used rather prominently in science already. But then there's others. As soon as you add in adversarial dynamics, you get into hybrid games, which are hybrid systems, meaning discrete and continuous dynamics overlapping with adversarial dynamics. And this is only one way of modeling the uncertainty, how the world can evolve. You can resolve uncertainty in the world adversarially, which means the world is out to get you. And sometimes this is what you need to do. And sometimes this is what you need to do even if the world isn't really out to get you. Even you only have to do that just for worst case verification reasons. So just for purely analytic reasons, you have to say, well, I don't know what the other robot is doing. Maybe the other robot is trying to hit me. Maybe it is not trying to hit me. I don't know what it's doing, but it certainly doesn't necessarily agree on the same goal that I have. So as I'm planning the way how I can achieve my goal, I have to expect that at some point, sooner or later, other agents in the field might interfere with the choices that I'm trying to do. And that takes you into this adversarial dynamics. But there's other uncertainty that is of a more stochastic nature. And in that case, what you're getting at is not discrete and continuous dynamics alone, but also stochastic dynamics, which overall then called stochastic hybrid systems and exhibit a behavior that can be as crazy as the one down here. But even these are not all the dynamical aspects that are irrelevant, because you also have distributed hybrid systems aspects, which are hybrid systems alongside with distributed systems married together. And for example, in a car control scenario, while each of the cars may be modeled reasonably well by hybrid system behavior, certainly that doesn't mean the whole highway could be modeled that way, because, well, for one thing, we can't even write down that many differential equations. I can't write down a differential equation for every car that's currently stuck on the key bridge here. But you have to take into account that all the cars are similar, and there's similarities, and there's a distributed systems aspect that is also going on at the same point in time. So fortunately, all those various classes of models for cyber-physical systems that share this common uniting feature of multi-dynamical systems don't just come as modeling principles, but they also come with answers. And they come with a family of differential dynamic logic as answers. So differential dynamic logic is the original one I introduced a little while ago, which is the logic of hybrid systems, which means it is suitable for specifying and also verifying behavior of systems with discrete dynamics and as well as continuous dynamics. So in this language, you can write down your system and a question about the system, and then you can use the differential dynamic logic also to answer whether this question holds true. For example, a safety property of a car or something like this would be modeled that way. As soon as you go into combination with adversarial dynamics, well, there's an analog logic which is called differential game logic, which is the same thing except that you're adding adversarial dynamics as well. So when you have those two robots, for example, moving around, this is what you will have to look at. There's a corresponding one in this family as well, which is called stochastic differential dynamic logic, which takes stochastic dynamics into account. Then there's one that takes distributed dynamics into account on top of the hybrid systems dynamics, which is then quantified differential dynamic logic. But I'm really just focusing on a brief glimpse of the base logic of differential dynamic logic, where I'm talking about hybrid systems. To give you a flavor of this is the programming languages view. A programming languages view on hybrid systems, where you say there's a very simple model. I only give you the bare essentials. I'm not interested in anything else. I only focus on the core elements, the ones that are really crucial. This is the bare language for specifying and modeling what hybrid systems do. There's discrete assignments. There's test conditions for probing the current state with respect to a logical formula that tells us whether they're true or not at that point in time. There's a differential equation as a fundamental operation, and I'm cheating a little bit. I'm hiding this part here, which in hybrid systems is not okay to do. It's the evolution domain constraint. But in hybrid games, it is okay to hide this because you don't need it. So I'm just going to take some liberties here and ignore it right away. And then what else can those systems do? Well, your system can be a non-deterministic choice of either the car in front of me is accelerating or it is braking. I don't know which one it's going to be. So I have to live with both outcomes of the future evolution of the world, and I have to be safe regardless of what's going on. Sequential compositions, which would just mean, well, first something happens, I don't know, maybe first the car in front of me speeds up a little bit, and then later on it slows down a little bit, and I have to be safe after this behavior. It's not okay if I just assume because the car in front of me was speeding up, it will do that all day long, because ultimately it might actually start braking again. Or steering left, steering right, same story. And there's a notion of non-deterministic repetition, which is the fact that, of course, you have control loops, and in regular expression language, all that this is actually a star. It's something that makes the system repeat any number of times because you never quite know when somebody's going to shut off the system, and you need to be safe regardless in all those circumstances. Now, this is the hybrid programming language. Take any of these operators away and it doesn't quite work any longer. Add anything extra and the answer is you don't need it because it can be defined in terms of the ones you have here. So it's really the minimalistic core of hybrid systems. Everything else is irrelevant. Now, that's your programming language of hybrid programs with which you can describe those systems. But of course, that doesn't give you any reasoning. That doesn't give you any specification. That doesn't give you any way of saying what is it that you want to be true about those various control systems. And that's where the logic comes in, differential dynamic logic, where I'm just focusing on those two operators back here, where you say, well, if alpha is one of those hybrid programs here, so it describes maybe my favorite car or airplane or something like this, And phi is a logical formula that corresponds to characterizing under which circumstance are they safe. Things like, this airplane has to be safely separated from that plane by at least 5 miles, otherwise we're in trouble, and things like that. Actually, it's just not quite that much. But in any case, you get the idea. Then this property here will say, well, all ways of running this air traffic control system here will be such that indeed the two planes are safely separated. And if this logical formula is true, you're happy because it means you can rely on your air traffic control maneuvers being safe. And if it's non-true, you're not so happy because it means don't even climb in the plane. This is the dual one, which says that some runs of your system reach a certain goal and things like that, but I'm not going to focus on it. There was syntax. Meaning is easy to find, fits on the slide, but I'm not going to talk about it. The most important thing for reasoning purposes is that you have what's called an axiomatization of this logic. And what that means is these are lots of axioms or lots of equations of truth. What they mean is that, for example, if you have a system that can do a non-deterministic choice, the robot in front of me or the car in front of me will accelerate or brake, I don't know, I have to be safe regardless. And if that's what my question is, I can rephrase my question, I can answer it in a different way, I can ask. So, well, for one thing, I guess all ways of running my acceleration case, when the robot in front of me is accelerating, have to be safe. Otherwise, I lose right away. And also, all ways where the robot or a car in front of me is braking has to be safe. Otherwise, I would not be happy. And then you say, well, but if both of those cases work out, then all ways of the system that has a choice of doing either of those two behaviors will be safe. So in other words, what all of those equations of truth tell you is that if you have a question about a slightly more complex system here on the left-hand side, then you can reduce it equivalently, which is what this equivalence operator here is all about, to a question about subsystems. Well, you do get more subsystems, you get many questions and so on, but each of them individually are easier. So you're making progress, which just means if you apply an equation of truth to whatever you have left and so on, you keep on doing this until you're done. Ultimately, you're going to be left with just very, very simple, very, very small systems, which is exactly what I meant by saying that multidynamical systems, characterizing that individual pieces come out of smaller fragments of the system, help us in taming the complexity of those systems because we're successively reducing questions about complex systems to lots of questions about simpler systems. And that's great because the simpler systems are by definition simpler. We can reason about them. Skipping over those as well. I'll share the slides so you can look at those. Here's, for example, a pictorial illustration of said axiom that I just talked about a moment ago, where you say, well, if this is what I'm interested in, I'm safe no matter which direction my system evolves to, then I have to be safe in all ways how the left evolution could happen, otherwise I'm in trouble. And I have to be safe in all ways how the right evolution can happen, otherwise I'm in trouble. And as soon as I know both of them, which means as soon as I know their logical conjunction, I know the original system must have been safe as well. And in similar ways, you decompose your system in all the other cases as well. Now, with this as a language, all of a sudden, you can do a programming languages and logic approach to that, and you can build your favorite theory around it, which is the following interesting result, that this axiomatization that you've seen, these I don't know, 10 equations of truth, completely characterize what's true about hybrid systems, which means they are a sound and complete axiomatization of hybrid systems relative to differential equations, or instead relative to discrete dynamics. Let me unpack that for you. What it means is hybrid systems are complicated. We know that. Discrete systems are complicated. We know that, called Turing machines. Continuous systems are complicated. We know that. You put them together to hybrid systems, it doesn't exactly get any easier, except in the following sense, because all of a sudden, from a proving perspective, from a reasoning perspective, from an understanding perspective, it doesn't matter whether we understand hybrid systems or whether we understand continuous systems or whether we understand discrete systems, because as soon as we have understood one of them, all the others follow. So where's the mystery? The mystery is here. We have a system. It's a complicated one. But we understand it has a simple piece. It's just a continuous dynamical effect. We have another simple piece. It's just a discrete dynamical effect. And we may have multiple of those. We combine them back together. Each of them are not so bad. Each of them are a little bit simpler. We combine them together into a hybrid system, which is, of course, as complicated as the original system. But the pieces, remember, are not so difficult. And as soon as we then learn that actually by this theorem, the theory of continuous systems is equivalent to the theory of hybrid systems, is equivalent to the theory of discrete systems, and every question on one side you can take and translate over into the other side. All of a sudden you've made a lot of progress, in particular because the proof, which is complicated, it's a 25-page proof or something like this, but it is constructive, so you can operationalize, mechanize these principles. So for example, if you have a question about a continuous system, a differential equation that is lingering around in your system, you can certainly say every question about a differential equation is a question about a hybrid system, just a very simple one. And that can be answered in discrete ways. So you can take your continuous system, translate it over into a discrete world, and answer it. You can take your discrete system, translate it over into a continuous world, you continuize it, and you can answer it. And all of these constructions are effective. In particular, this means, because these constructions are effective, induction is the premier weapon against discrete systems. In the sense of induction is the way how we convince ourselves that discrete systems do what we want them to do. And because every verification technique, every analysis technique lifts over into hybrid systems, also into continuous systems, what you learn from this is that there has to be induction for differential equations. And indeed, that's possible. Here is the answer. It's called differential invariance. And the reason is the following. The reasoning is the following. You're plotting the vector field of your differential equation. You have your differential equation. You're plotting the vector field of a differential equation. Of course, you could answer questions about them by following the global solution and answer whatever goes into the bad blue region. Trouble, you have to start your differential equation in each and every of those uncountably infinitely many states and check at every uncountably many, infinitely many points in time whether it's bad or not. Bad way of doing it. So instead, you follow the vector field. You say, if my vector field never points from safe into unsafe, then as I follow it, I can never get into any unsafe state. Likewise, there's a fundamental proof principle called differential cuts, where you say, well, if my system can never make it across this red boundary, which means it can never get into this red region here, I might as well cut it out of my state space. If it cannot make it across this red boundary up there either, I can cut it out of my state space. And then you look at the state space and says, somehow my unsafe states have gone, which means by definition my system must be safe. I'll skip over the differential ghost story, which is kind of amazing as well, and I'll skip over this one, which is an equivalence characterization of all algebraic invariants of differential equations. To mention, is that any good? In practice. Now we've got lots of beautiful theory, lots of concepts, lots of logic, lots of principles that characterize the fundamental principles. Does it help in practice? Yes, it does, because, for example, you can do railroad. The European train control system is what that is. There is interesting maneuvers of aircraft collision avoidance and so on, also a direction that we're following up on with the FAA. My students have been extremely creative at verifying lots of very interesting properties of highway control and CICAS, collision avoidance, no, hold on. Intersection control for cars. I keep forgetting what it stands for. Various interesting collision avoidance maneuvers for planes, also UAVs with arbitrarily many of those. Ground robot motion can be verified to be safe. The dynamic window approach. Surgical robotic systems can be verified to be safe this way. This is a study with the Johns Hopkins University Applied Physics Lab, and so on. So all of these things can be done. But what I personally like even more is that there's many interesting systems that can be verified by undergrads. In this Foundations of Cyber-Physical Systems course that I introduced in the fall of last year, I taught the students everything about analysis and design and logic and so on and proofs about those systems, and all of a sudden the students were able to verify many interesting, challenging scenarios of robot control, and not just build their own controllers and model their own systems, but actually come up with proofs why they work, safety proofs of running a robot down on the corridor, for example, and things like that, and many beautiful extensions of those. By the way, if you're interested in courses or so, there's it took me forever to write down lots and lots and lots of lecture notes at a level that the students, undergrads, can understand and so on. But now they're done, and you can look them up on the webpage if you have some undergrads that you want to refer them to. Wrapping up, what you've seen here is the logical foundations of cyber-physical systems, with the idea at the heart of that being that actually what cyber-physical systems are, from a truly fundamental perspective, are multi-dynamical systems. They combine discrete dynamics, continuous dynamics, adversarial dynamics, non-deterministic dynamics, stochastic dynamical effects, all together. Each of them are simpler dynamical effects, but because you realize that, all of a sudden you tame their complexity by using compositionality, which is what logic is great at. This is a logic and proofs approach for cyber-physical systems with a lot of elegant, beautiful theory and so on, but also some interesting applications that has been implemented in the Chimera prover. And of course, there's lots of logic and computer science and math and all kinds of areas that go into this. But this is part of the fun. That at least if you ask me, hybrid systems and all their extensions are excuse to do your favorite math and still have people care because you solve their interesting practical applications that way. And with that, I guess I ought to stop and give you a chance for questions or Sriram to set up.
Maybe while Sriram sets up.
While Sriram is setting up.
Thanks very much. So maybe one question while Sriram plugs his laptop in.
Can you say that again?
Nonlinear differential equations.
Of course, differential algebraic equations, nonlinear ones, differential inequalities, differential equations with disturbances, lots of interesting things can be done as soon as you look at this. Yes, yes, differential invariants have some similarity to the Lyapunov thing, except they're for safety and so on. That's where a lot of this control things and so on comes in, which I might have erased from the slides.
Great. All right. Thanks again. So I have a really quick bio to give for Sriram as well. Since I spent all the time making up these bios, I should probably actually go through
So
them.
I'll have a challenge for him to pronounce my last name.
Sriram Sankaranarayanan.
Perfect. Wow.
I spent like an hour last night in my room. Not actually. He graduated with a PhD in computer science from Stanford University in 2005, and he's now an assistant professor in the computer science department at the University of Colorado at Boulder. From 2005 to 2009, he was enjoying life as a member of the research staff at NEC Laboratories. His focus now is on reasoning about hybrid dynamical cyber-physical systems, which model discrete programs interacting with a continuous environment, modeled by ordinary differential equations.
Thank you. Thank you for that great introduction. I must say, I did enjoy life at NEC Labs, but since I started at University of Colorado at Boulder, I had the CPS grant funded in my very first year there. And since then, my enjoyment of life has just taken off. Okay, so this is a CPS grant that has a very interesting title. It says, Analyzing Human Interactions with Drug Infusion Pumps. And the person you see there on the right is me. That's how I looked when I started at University of Colorado. And the other person is Clayton Lewis. Clayton's a cognitive psychologist. He works on human-computer interaction. Very famous person in that field, actually. Very famous pioneer in human-computer interaction. Trained as a psychologist and then as a computer scientist. So when I started, Clayton, took me for one of these chats, and then he said, what is a cyber-physical system? And I gave him the standard explanation. It's a merge of computational elements and a physical subsystem. And then he asked me a very simple question. What do you do about human beings? Does your theory have any place in it for talking about the human operators inside a cyber-physical systems? We can do all the great verification, and Andre gave us an example of all the wonderful kinds of system he does, but then the question remains, what can you do with humans? When humans are in your system, what can you do with human beings? And if you look at every cyber-physical system, the role that's played by human operators is very important. The success or failure of the interaction is decided by the human operators in the system, right? The automation plays a role, but the humans also play an important role. Mistakes are common in these interactions, and humans make mistakes. And there are certain kinds of interfaces that can amplify human errors and cause system failures. We've read about 3 Mile Island and all these famous disasters that have a combination of human mistakes that are compounded by series of unfortunate events to lead into catastrophic failures. So we wanted to study all of those. We wanted to answer questions like, what are the common operator mistakes that can be anticipated when you're designing a system? And what's the impact of a combination of operator mistakes on the overall safety of the system? And these are the kinds of questions we wanted to answer. So we wanted to answer this by essentially modeling human beings, like taking a human being, put them into a hybrid system, and use our verification methodology and so on. But that's a joke. You really cannot take a human being and model them into a hybrid system, except when you build some very controlled situations. You could probably start studying human beings in that nature. It's not doable. Humans are incredibly complicated. Human cognition, we are still understanding human cognition, but maybe we can make a start on this problem, make a small dent, and that has useful applications. And that was our overall approach to this problem. So we focused on infusion pumps as our beginning application because we thought the interfaces were simple, the interactions were relatively simple among the class of systems we looked at, and more importantly, we could get information about these. So if you wanted to go work in a nuclear power plant, they will not let a person like me anywhere close to a nuclear power plant, and I wouldn't want to go anywhere close to one either. So this is the kind of system where we could work with medical professionals who are very happy to give us information about their system. So we chose this testbed as something to study. And so let me give you a brief explanation of the kind of work we have done. I'll just take you through a tour of two important results that we have achieved. And if you are interested in more details, I'm happy to talk about it at the end when during lunch you can ask me about it. So we studied interactions at two levels. Interactions at the system level, and I'll explain what I mean by that, and interactions at the interface level, and I'll again explain what I mean by that. So let's understand this at the system level. So I arrived in the airport today and I wanted to purchase a ticket to get here. So at the system level, I go next to the ticket machine. You guys have seen that in DC Metro. I find the fare to get to Roslyn and I select a ticket purchase for that fare and I pay for my ticket and I get a ticket. So that's at a high interaction level, at the high system level, that's how it looks. But then if you go deep down, how do you select the ticket purchase for that fare? You press the up dollar key until the dollar amount matches with your expected dollar amount, then press your up send key. And that would be at the interface level where you're pressing keys, observing things that are happening in the interfaces. And we wanted to capture things that were happening at both levels. We wanted to capture things at the high planning levels, and we also wanted to capture things at the level of press a key, observe what's happening at the display and so on. And so we approached our work from both ends. So first, let me talk a little bit about system level interaction analysis and use insulin infusion pumps as the motivating example for doing this analysis. Okay, so when you talk about insulin infusion pumps, I have to introduce what they are. So type 1 diabetic patients are patients who lack the ability to, more or less lack the ability to secrete insulin. So they need external insulin that's administered by this device called the insulin infusion pump. And they have a continuous glucose monitor that measures their blood glucose readings. So the way this works is a patient knows about what they are planning to do, what kind of meals are they planning to eat, what's the amount of carbs in their meal, what is it, pasta or is it going to be steak, what kind of glycemic index does the meal have, and based on that and their current glucose, blood glucose levels, they have to decide an insulin bolus, a shot of insulin that's going to control the meal that's going to come up. Okay, it's a very interesting control problem. And if you look at it, the things that they are trying to avoid are two. Hypoglycemia, where the blood glucose levels fall so low that they could go into coma, and if they let it happen, they may even die. It's very dangerous. And hyperglycemia, where they could end up in the emergency room if it's really bad, but over the long term, they could get into kidney trouble, eye trouble. So if you want safety critical, this is really safety critical. You know, the patient's life, their longevity depends on how well they are able to use this pump to control their blood glucose level. So it's a great example for what we would like to analyze. So we started looking at this problem in great detail because it's a great example that's something that's safety critical. We didn't think it was too complicated that we couldn't model it. So we started doing that. Okay, and just to reiterate, the safe operation means that the patient needs to maintain their blood glucose level. And the interesting thing that's happening is here you can view it as a feedback control system. And the feedback here involves human cognition as your feedback. Human cognition is the controller. Okay, so the human is executing a control task through his or her cognition, really. And the human is controlling their own body, their own insulin glucose system, which actually has a feedback on their cognition, but that's too much for us to model. But it's a very interesting example of a problem that safety critical lives depend on it and amazingly complex at whatever level you want to study it. So we loved it. And the kind of errors that people make are well documented. Standard errors are carb counting errors. Person doesn't count the amount of carbs correctly. Insulin bolus timing error. Timing is really critical. So your body absorbs the insulin at some rate, and your body absorbs the food at some rate. And what you have to do is match the peaks. The peak rate of food absorption must match the peak rate of insulin absorption, and then you get perfect control. And if the peaks stagger, then you start to get really bad effects, as we will show you through our analysis, right? Okay, so the overall question is, how does a single mistake affect the overall safety of the interaction? Safety meaning maintain the blood glucose level within a range. Or how do combinations of these, because we are able to automate this process, we can now start to talk about Boolean combinations of faults. Fault 1 is present, fault 2 is not present, fault 3 is present, and build things like fault trees using whatever analysis we do. So we started to look into this. And the first step is to model this whole interaction. And so we started building models. So we built a model of the insulin glucose regulatory system, which is based on published models. There is a lot of published models since 1979, starting from Bergman's work. There has been a lot of work on modeling the human insulin glucose system. It's nonlinear, it's complex, but it can be modeled. And people have done a good job of modeling it. The latest models are the Havorka model and the Dalla-Mann model. There is even a commercial simulator you can buy if you're interested that simulates the human insulin glucose dynamics, has been approved by FDA for testing devices. So it's a great field to work in because this is available. The most challenging thing for our project was, how do we model insulin infusion pump usage? How does a user calculate how much bolus they need? And here, what we did was we looked at published material for training users, because users require a lot of training to use this pump. You just can't give a pump to a diabetic patient and say, go use it and live long and be happy. The chances are they're going to do something really bad to themselves if you do that. So there is extensive training involved. So I personally looked at the manuals and went through the training myself, even though I am not diabetic. So I still went through it. Consulted a lot of endocrinologists, talked to physicians. Internet is a great resource. I read blogs, looked at a site called Patients Like Me. And then the books I consulted was, books like Think Like a Pancreas. I read through the book. And through the book, I read and I curated a model of how a person is ideally supposed to use a pump. And then I built this whole model in Simulink and Stateflow, and we had a Simulink Stateflow diagram which has nonlinear dynamics, has 12 state variables, 10 modes, lots of external disturbance, meals, sensor noise, user errors. And so this model is really complicated. So we went through all this effort and built a complicated model. But then my other research happens to look at how can we do something with these complicated models. And so this meshed up very nicely with that research. And so we were able to use a tool called S-Taliro, which is not going to be the subject of my talk, but we use this tool to analyze this model, to look at falsifications, be able to work with this model and violate the properties. So let me explain what S-Taliro does on this model. So what S-Taliro does is it searches for worst cases of hypoglycemia, low blood glucose levels, hyperglycemia, or failure to settle after a meal by trying all possible combinations of faults, all possible timings between the faults. It just tries this infinite space of faults to figure out what are going to be the worst cases, and does so in a global optimization framework. We just throw in heuristic optimizations, we have a robustness metric, and it tries to analyze these and finds out particularly bad cases and just isolates them. So all we need is the ability to simulate the model, and then we are able to use this tool. So we did that, and just to give you an idea, we came up with lots of scenarios under which a person could go hypoglycemic, scenarios under which a person could go hyperglycemic. In fact, for hypoglycemia, we found there were 2 scenarios for hypoglycemia where the person has the insulin too early or the person has the insulin too late. And we had multiple scenarios for hyperglycemia, and we found lots of combinations of faults that have a signature, and very specific signature that when you see it, you actually know that the likely fault that occurred was the fault that was predicted by our model. we went online, talked to people, and they agreed that these were actually accurate. These were actually reflective of what happened to them when they make these kinds of faults. So this is great, but the question is, where is the application? Well, one application we are looking at is personalized modeling and diagnosis. So if you can do personalized modeling of a patient's personal physiology, I'm using this term loosely, but if you can take data from a patient and try to identify a system that explains their insulin glucose response, which is not hard to do, then you could start to do things like this. You could take the patient's data log over time, and a patient could come to the doctor and say, doctor, I'm unable to keep my blood glucose level under control. What am I doing wrong? And previously, the doctor and the diabetes educator had to pour through the charts to figure out what they were doing wrong. But now we could do it with software. If we build this personalized model, which we are attempting and many groups are attempting to do, we can now bridge the gap and actually have a system that can advise patients, and they don't have to go to a doctor. They could have it on a cell phone, right? And it could give them some advice. Of course, these are not systems that we could deploy on patients just like that, but at least we have made a start towards building systems like these, and that's great for us. Okay, and let me quickly summarize work on interface level interaction analysis. So remember, at the interface level, we are looking at the key presses, the individual key presses that you need to do to get a task done. And at this level, there are things that we are worried about, things like mode confusion in the devices, interface inconsistencies, missing confirmation before action, and these are all interface level issues, and there is lots of good work on identifying these issues. So the question then is, if you're given an interface, how do you find out the internal state representation of the interface? And this was a big problem for us because these interfaces can be written in Android, they can be written in Swing, they can be written in Java, they can be written in a lot of languages, and we had to build a static analyzer in these languages to get to the interface, the internal user interface state machine. So we did a different approach. We went through computer vision. So we took a wonderful little programming language called Securely Script, which is able to interact with the interface on a simulator. So you could run your interface in an Android simulator, and the script takes control of your mouse and does screen capture and does computer vision algorithms to recognize where are the keys, and it presses those keys and it simulates the interface just like a monkey presses a key. So it just keeps pressing keys and sees what happens. And then we were able to use an automata learner using an idea that's kind of old. It's called grammatical inference. So we look at the interface action on the back end, we look at the logs, and we are able to learn a finite state machine and model check this finite state machine for interface bugs. So we did just that. And the kind of model checking we do are for things like mode confusion, interface inconsistencies, and I can explain these, the bugs we found if you talk to me afterwards. So let me just give you an idea of what we find. So we actually took this interface, since we don't have a robot arm that can press the keys in this interface, what we did was mocked up the interface. So we took the interface of a commercial infusion pump model, and one of my students mocked it up in Java. And once we did that, this is hard to see because it's kind of big, and I don't want you to focus on it. We learned a state machine. And then we model checked the state machine, and we actually found mode confusion errors. We found that the state machine of most commercial infusion pumps have some mode confusion errors. The question is, are they harmful? Are patients being harmed by this error? Has someone been fooled into doing something wrong with the pump by these errors? That we don't know yet, but at least we are able to find them, which is at least a little bit of progress for someone like me. So what are we doing for future work? Well, our ambitions are sky high. So right now we are starting with infusion pumps, but ideally we would like to look at ventilators. We would like to look at anesthesia machines. We would like to look at situations where there are multiple people working together on a machine, on an interface, trying to achieve a set of common goals. Because there you get to concurrency issues between humans. You will have communication between two humans. You will have the individual knowledge versus the group knowledge problem, which we look at in modal logics and in many kinds of problems, and they will start to appear in a very interesting way when you have multiple humans who are interacting with each other. And this is something that we are really excited about. That's something that we would like to move forward, something we would like to trouble our NSF program managers with. The other kinds of work we are looking at are automatically diagnosing faults. So looking at trying to generalize the work we have done with insulin infusion pumps to other interfaces where we could do auto fault diagnosis, try to improve the usage, try to predict harmful usage patterns, detect harmful usage patterns, and so on. And so finally, I would like to end by thanking CPS for allowing us, the NSF CPS program, to allowing us to work in this really fascinating area. Because the one thing I can say is, even if you agree or disagree with the impact we have had, the thing that we learned is fascinating. We just learned a fascinating amount of stuff from human insulin glucose system, pharmacokinetic modeling, grammatical inference, computer vision algorithms, cognitive science. I never imagined you could do so much in a single grant and credit a single grant as the funding source for so much work that in such a vast variety of areas, and that's great. Introduced us to a great set of collaborators. I have just listed a few of them. Tom Ye for one, Georgios Finakos, and this is very important for us. We are constantly growing our set of collaborators, trying to look for people in the medical school to work with us, be more involved in our grants, and this has been the seed for us doing that, going there and talking to them, and so on. So if you would like to learn more about us, just Google for Infusion Pump Analysis CU Boulder, and our page should be the first one that pops up. You can look us up at pl.cs.colorado.edu. Thank you for your attention, and I'll take any questions if you have them.
Questions?
How do you generalize the applicability of your algorithm? Because just now we were saying that wide range of applications for the CPS size. So how do you convince the reviewer in proposal that you have a wide range of applications?
So I would say in our case, we were honest and upfront. We said human cognition is so hard that we will make some progress on some of these fronts. And the hope is that, if you look at infusion pumps, then there are drug infusion pumps, there are insulin infusion pumps. So we looked at a wide range of applications for infusion pumps. So I want to be scientifically conservative and say that, yes, some of this can be taken to other interfaces, but I also want to protect myself and say, human cognition is so hard to understand and so hard to model that I think, any advance you make in any particular domain, I think is valuable. And personally, that's all we said in our NSF proposal, that we will look at this problem and we will look at infusion pumps to guide us and focus our work onto something to ground us. And somehow the reviewers bought our story. I mean, that's all I can say. We were happy and surprised, but they brought our story. That's all I can say.
So before this formal model came into the picture, right, before you started with this formal model, how were the systems verified? What is the current way for doing? I mean, this is
Right. So I can give you one. I can cite one source. I was looking up a news article in a medical device trade magazine, and the headline was, this was in 2010, I think, and it said FDA urges medical device manufacturers to do model-based testing. So essentially, in 2010, they were trying to convince medical device manufacturers to do modeling and model-based testing. My personal understanding of how medical devices work is, it's a very closed world. They have a lot of experience doing these kinds of devices. Every device is an improvement on a previous device, and so they have survived a long time without having to do much modeling. Based on their know-how, their extensive experience, they don't go through this kind of formal modeling. But it's just now that FDA has been trying to get behind these medical manufacturers, device manufacturers, and say, you have to do modeling, you have to do some amount of verification. And by verification, they just mean simulation. So my 2,000 feet opinion is they are not doing much of this, or even if they are doing, it's just starting to be done. It's just starting to come out.
All right, thanks very much. Okay, so we're going to live bravely on the edge here. Can you hear us now, Hadas?
I can. Can you hear me?
Good. I'm just going to make sure we don't have too much echo in the system before I walk away from my machine. Say some more things.
Oh my gosh, there's ice flying outside of my window. So I can hear it boom every once in a while.
Nice. Okay, so I'm going to set you right here so that you, if it occurs to you to look at the audience, that you can see the audience.
Okay.
All right, and in the meantime, I'll give a quick introduction, and then we'll just turn it over to you.
Okay, sounds good.
Great. So our final speaker, who couldn't, obviously, you might have guessed she's not available to join us in person. But she's still able to give us some of her ideas that led to her successful career proposals and to her other CPS proposals. Hadas Kress-Gazit received a PhD from University of Pennsylvania in 2008, where she developed methods to create robot controllers that are guaranteed to satisfy high-level tasks as part of the GRASP lab. She's now an assistant professor in mechanical and aerospace engineering at Cornell University, and her research and teaching interests include robotics, motion planning, task planning, model checking, verification, hybrid systems, language for robotics, and human-robot interaction. So I'll turn it over to you, Hadas.
Great, thanks, John. Again, my apologies for not being there in flesh, but in spirit. So I'm just going to start my talk. I don't know if I'll be able to hear any questions along the way, so hopefully Jonathan will be able to tell me to stop. I'm happy to take a away. I'm going to share my screen. Okay, just let me know.
Okay, I'm going to try an experiment to turn off the video from our end.
Okay.
How do I do that? Hide?
In the Hangout, so there's
Mute? Say some more stuff.
So can you see my screen now? So I have my slide.
Yeah, I think we can see your screen. The problem is I think that there was a sound problem, but it may have gone away now.
But now you've muted it, so she can't hear you. She cannot hear.
Damn it!
Okay, good. So I wasn't actually looking at the screen, so okay. All right. So again, my name is Kress-Gazit. What I want to do is first tell you a little bit, big picture, what my research is about, to give some context. And then I want to talk about results from a CPS program that just completed in September. And I want to talk to you a little bit about, kind of give a teaser for a CPS program that we just started in October. So I've been lucky in getting consecutive different projects, they're very different projects, but again, CPS projects. All right, so imagine you have a robot. This is a robot in my lab, it's Aldebaran now, and you wanted to pick up balls or pick up red balls from the ground. Great, and then maybe, you know, have a robot, you can do a lot of things with it. So then later on, I want to put it on a Segway base, and I want it to go around the office building and, you know, deliver letters. So how is this usually done? This is usually done by having someone have some notion of specification, kind of idea of what they want to do. But really what the person sits down and does is writing an implementation. So they figure out, they have an idea of what they want to do, but they actually sit down and write how it should be done. And then they test it, and I only heard the last few thoughts of the previous speaker, and basically said, you know, how do you verify something? Well, you know, sometimes when they say verification, it's actually testing. So in robotics, it's the same. So you implement something, you think it works, and then you test it a bunch of times. So it doesn't work the first time, usually. So you debug it, you fix it again, and then you test it again, and then at some point, you're kind of confident. You're saying, okay, now it's going to work. Is it actually going to work? You know, in most cases, yes. Is it guaranteed to work? No. Are there any bugs? Maybe. You really can't tell because there's no notion of, you cannot provide guarantees when you're testing implementations. So that's kind of one thing that's kind of, what's usually done in robotics, kind of high-level planning. Now, what happens if I want to have the robot drop balls in a bin, and then 5 minutes later, or 10 minutes later, an hour later, put it on the Segway base and go deliver letters? How do I quickly change between these two tasks in a way that will not require me to rewrite the code and test it and a week-long hackathon to make sure that it's doing what it's supposed to do? So for that, what my research group is about and what I'm advocating is really moving the abstraction up a level, being able to provide, to talk about behaviors and talk about robot specification at a specification level, not at how it should be done, but rather what should be done. So, go deliver the letters in Upson, which is the building we're invested in. And then what I want to have is machinery that automatically is guaranteed to provide a correct by construction solution, a correct by construction controller that's guaranteed to work. So it's not that I'm hand building something and testing it, but rather I'm automatically synthesizing a guaranteed to work solution. Now the asterisk I have there by the synthesis is sometimes I can't. Sometimes the specification doesn't allow me to find a controller. So I want to be able to provide feedback when that doesn't happen. So what could be the problem? What is fundamentally problematic in my specification that doesn't allow me to generate a controller? So that's kind of a lot of my research is on how do I specify these specifications? What is the language for these specifications? And we have some work on connecting natural language and structured English, which I'm not going to be talking about. And then a significant portion also of my work is really what is this black box and how does it relate to the field of robotics? So how do we deal with the fact that we have physical systems, we have continuous aspects, we have discrete aspects, and we have, they're working with humans. How does it all mesh? And how can we provide any guarantees? So, okay. I'm flipping between to see that it's hard to tell, I can't hear you guys, so it's hard to tell if you're still, they haven't been disconnected. All right, so to give you an idea of the approach in a nutshell, of how do we do these things? How do we provide guarantees? How do we synthesize controllers? So the idea is we abstract a continuous problem, which in this case is sensing and actuation for a robot, into a discrete one. And the way we do that, we create propositions, and the formalism that we use is linear temporal logic. I'm not going to go into really what it is, but if Andre didn't talk about it, which I guess he probably didn't, the idea here is we have propositional logic and we add some temporal modalities, very, very loosely speaking. So I can reason things about things that should happen next, things that safety properties, things that always should happen, liveness properties, things that eventually should happen. So if I have a robot and I want it to go deliver letters, so eventually it should be at an office in which it has to deliver a letter, and always it has to avoid the walls. Those are just examples. Once we have a specification, then we solve for provably correct discrete controller. If one exists, we can provide guarantees that one exists. Or if we, the synthesis idea is to create a system such that every execution of the system satisfies the original specification, if such a system exists. Now this is discrete by nature, so we have a logic, then we have a state machine that represents the system or the controller, and then we have to continuously implement that. And there are a lot of questions that come from the fact that it's a robot and transitions are non-instantaneous, and all the physics that come from that approach. And a lot of my research is along those lines. But just because I don't have a lot of time, and we're really in the business of what is the CPS program, what have we done for that? So let me give you an example of what the CPS program is. And Jonathan, I need some cue from you that at some point that you'll see the video, but if not, that's fine. So imagine we have a task. This is a task that I'm not going to go into the details of this task, but you can see there are corners, and then there are kind of paths between the corners of the workspace, and there are cones there. And there's a fairly complex robot specification, but ultimately the robot is supposed to not go into an area if it sees a cone. So it cannot go through the aisles if it sees a cone. This is what happens when one of the times we ran that experiment. I can't really tell if you're seeing this. Can you see this? I can see you guys, so thumbs up. Oh, thank you, great. How slow. Okay, so hopefully you kind of started at the same time. That was Cameron, who was one of my students. What happened here is that the robot controller was correct. The problem is it didn't sense the cone. So does that make the behavior correct? Does that make the behavior incorrect? I mean, as far as the robot is concerned, it was fine. It didn't see the cone. It walked into the area. But as far as someone looking at it from the outside, it did something unsafe. So the problem, one of the problems that come up from this type of approach, when you talk about robotics and you talk about physical things that have to sense their environment, is that you'll have a lot of errors. So you might have false positives, false negatives, there's a lot of uncertainty. And the question is, what can we say when we have uncertainty? So the first CPS that I had, which was in 2009, and basically ended in September, was on the topic, well, it was a collaborative effort with 2 more PIs at Cornell. And the title was Tightly Integrated Perception and Planning and Intelligent Robotics. So the idea there was, how do we combine the probabilistic nature of sensing and into this kind of formal framework in a way that meshes well together? So what we did, and I'll just kind of to give you a feel for what we did for this project, is we said, all right, we have this problem that sensing is inaccurate, and we're assuming to be able to generate a controller, we're assuming sensing is perfect. Now there's obviously a discrepancy there. So we said, okay, let's synthesize a controller assuming everything is perfect, and now let's basically verify whether, or use probabilistic verification to get bounds on how likely is it for the robot to satisfy a task. So what we did, we created this big model that's composed of environment probabilities, so how likely am I to see something, sensor uncertainty, the probabilities of false positives, false negatives, and then actuation uncertainty. And we compose this all together with the synthesized controller. We compose it into a big model, a big probabilistic model. And we use model checkers, for example, PRISM, which is a probabilistic model checker, to figure out the probability of satisfying the specification. So now I can't say, well, now if I know that my sensor is likely to be 90% accurate, then I can say, you know what, with a probability of 80% within 50 time steps, you will not collide with another vehicle, for example. And I use the example of vehicle because it's going to show up in a second. Another thing that we did was say, this is an analysis kind of approach. So we did a kind of an analysis approach saying, what can we say about the likelihood of success? But also we use this analysis to be able to suggest changes to the specification that will make the task more likely to succeed. So we can think about adding safety specifications. So maybe there's, if I restrict the robot's behavior a little bit more, maybe it can still satisfy the original task, but now it's less likely to fail. It's not because it's not going through a dangerous region, for example. I might be able to restrict initial conditions. So maybe I didn't assume that the robot starts anywhere. It can start anywhere in the workspace. But if I say, you know what, it can't start in this pit, then I'm more likely to succeed. So this analysis lets us provide, go back to the user and say, you know what, if you change these things, you're most likely to succeed. Now, nice things that comes from this, it's not just the task, but also if there's one sensor you want to improve, it will tell you which sensor is the best to improve. If you can spend some more money and buy a better, whatever sensor you want to put on the robot to get a more accurate sensing information, then this is the one you should use for this task, to make it more likely to succeed. So those kind of the type of things that we do. Now, a lot of times when we think about these approaches, the probabilities, you don't really know where they come from. There's a number. So we can work with any number that they give us, any probability distribution, but where does it really come from? It should come from some, thoughtful representation of what's going on in the world. So in collaboration with Mark Campbell, who's my colleague here at Cornell, my student and his student basically sat down together and said, okay, let's look at the situation in which we're talking about autonomous vehicles. So Cornell has an autonomous vehicle that was finished the Urban Challenge a few years ago. And the idea is, let's try to model or anticipate the behavior of other vehicles in the workspace. So I can see a vehicle, for example, in this case, the bottom red vehicle on the left-hand side, or on the right. The bottom red vehicle, that's the Eagle vehicle, so this is the robot. And then the blue vehicle on the top is the one that's the obstacle, the other vehicle that you're not controlling. And you can kind of anticipate where it's going to go. So these probability distribution, it's a Gaussian mixture. Using the Gaussian mixture model, we can kind of anticipate where the robot can be. And from that, we can provide probabilities of how safe it is for the robot to cross an intersection. And using these probabilities of safety and thresholding the safety, then we can analyze the probability of success of the mission. In this case, the probability of success means no collisions. So this is really, we looked at what a framework that allows both the anticipation and the sensing, and the formal method, the high-level planning based on the formal method, and they very naturally fit together. Because we can, and then we can look at the trade-offs between different probability thresholds and different tasks and different restrictions and all that. That's kind of work that we're doing, and the last thing that remains to do is actually doing the experiment with Skynet, which is the autonomous vehicle. We're kind of waiting for all this ridiculous amount of snow to thaw out, so we have a place to work. So this was and we have, this project was the previous incarnation of CPS, there were small, medium, and large. This was a medium, and together also with some computer vision researchers at Cornell. So there are a few other aspects of this project I'm not talking about. But what I do want to mention is the next project that just started in October. So this is the project in collaboration again with Mark Campbell, who's one of my colleagues, and also Mark Hume, who's from the University of Pennsylvania. So he directs the mod lab. And the idea there is, assume we have these modular robots, and Mark Hume is well known for building these modular robot systems. How can we develop a framework that allows us to control these at a high level? So what does it mean to have a specification for a modular robot? So now we can talk about sensing, we can talk about motion, but we can also talk about reconfiguration. So now we can change the morphology of the robot itself. So we can, now we have to, there's another dimension to think about when we're doing this high-level planning, and another dimension to think about when we're developing what a specification should be in this case. So we're kind of starting out. The main idea here is kind of to build this library of controllers that allows us to compose things together. Then you can have guarantees on basic building blocks of the library and guarantees at the high level. The top row of images is different things that Mark Hume has done with these modular robot systems. So you can see the middle one is, the left, the one on your right and middle is a robot opening a fridge and taking out a juice box. Now that was teleoperated, so there was someone controlling the robot from afar. The idea is for us, for this project, is to automate that. Be able to tell the robot, go get juice from the refrigerator, and have it do it autonomously. And we're, as I said, we started a couple months ago, so we're working on this. So that's about it. This is kind of just a taste of what we've been doing, especially in the CPS program. And I'm happy to take any questions if I can actually hear you. Thanks. And you're still muted, so.
Yes. How's the sound now? Better?
Now it's perfect.
All right, good. So thanks very much, Hadas. We have some good time for questions. I think she has to leave in about 4 minutes to head to a meeting, but years of time for a question. Yes, I'll repeat it. Where do you get your environmental probabilities?
So in the project that we did,
I had to mute you, sorry. Sorry, I have to mute you whenever you talk now, so I'll let you give the answer. So how do you get your probabilities, and then I'll mute. Hold on, I did it backwards. This is why this is not my job. Okay, how do you get your probabilities?
that I heard. Okay, now I can see that you're muted. Perfect. So how do I get my probability? The idea is we collaborate with people who do sensing. So I don't do sensing. And for example, in this case, Mark Campbell, he does a lot of work in terms of sensor fusion and probability distributions. And in this case, anticipation was, we assumed some dynamic, well, Mark and his students assumed some dynamic model for the vehicle. And it's very constrained because we are assuming the vehicle won't go off-road. And based on these, on the dynamics and on the sensing information that we get, we can create these probability distributions. And those basically feed into the high-level planning and for the analysis and the synthesis. So, but that's that's all. In general, that's an awesome question because finding these probabilities is not easy. And, yeah.
All right, maybe time for one more question. Does the methodology allow for sensor faults?
Yes and no, right? So, yeah, so the methodology right now, since the analysis that we're doing is assuming sensor fault. If the sensor is perfect, then the synthesis is already done. What we're working on right now is actually synthesis, so we can create kind of the most likely to succeed controller. Now, if you want to have the robot kind of go into a fault state, you can specify that. So that kind of is up to you at the high level. If you want to say, if something happened that I wasn't quite expecting, what should happen, we can definitely model that. And we can model, there's a little more details, so it's kind of hard to get into all these details kind of in a 2-minute answer. But we do have, in the synthesis, ability to recover from environment violations, if you will. So if you're assuming the environment will do one thing and it suddenly does something different, then we have ways to recover from that. But that's not so much a sensing, that's more of an assumption question. But we are able to, we can model some fault, but there's some things that we just can't model, because if the robot can't see something, then we don't know it's there.
All right, well, let's thank Hadas one more time. We should do this again sometime in about an hour and a half or 2 hours. So I'll make sure that I get in the loop with you to hook back up again when the time comes. And in the meantime, everybody else, go eat as much food as you possibly can. We'll probably be doing some informal exercise in here around 12:30. So it'll be based on an exercise that one of the CPS aspiring PIs submitted an idea for a group work. So it's not enough that all 100 of us could do it, but some of you who are really passionate about the idea could do it. And it's going to be sort of refining an idea that could be a breakthrough idea. And so if that's something that's interesting to you, come back into the room at about 12:30. That gives you about an hour or so to eat, and then we'll workshop it out somehow. All right, thanks everyone.